Okay, in the last part, I will start to talk about the reliability challenges in more and more device. In this case, I will bring the example in the GaN, gallium nitride, and silicon, wide bandgap technology, and describe their reliability challenges. And some of the reliability challenges are very similar to the previous mentioned related to TDDI and BTI and interface charge. These are also happen in the gallium nitride and silicon carbide as well. But of course, there are some additional reliability issue. For example, in gallium nitride, there's a very well-known what we call the dynamic R-on issue. And in silicon carbide, we also have to be worried about, for example, the different TDDI mechanism, because the silicon carbide device usually have very thick dielectric rather than the advanced CMOS. So therefore, the TDDI mechanism can be different compared to the advanced silicon-based technologies. At first, I just quick overview that what would be the difference between the gallium nitride and silicon carbide technology compared to the typical silicon. And we can analyze three material properties from the bandgap, from the critical electric field, from the electron mobility. So we can find out that consider the bandgap. Silicon carbide gallium nitride has a 3 times larger bandgap than the silicon. And considering the critical electric field, silicon carbide gallium nitride has a 10 times larger electric field than the silicon. And also in the electron mobility, although silicon carbide has a low electron mobility, but the gallium nitride has a high electron mobility compared to the silicon. So here is a summary like it's shown. We have a 3 times larger bandgap, 10 times larger critical electric field. And if we try to plot the R-on versus the breakdown voltage, and we can find out that the silicon theoretical limitation is shown here. So that means if we try to fabricate the 1000 volt power device, the on-resistance for the silicon will be around 10. But if we use a silicon carbide or gallium nitride, we can see that the on-resistance can have the 2 order or even 3 order reductions. And in the end, that's leading to the very great the RDS reduction. As I say, we have the 2 order reduction by using the silicon carbide, 3 order reduction by using the gallium nitride. In the end, when we use the silicon carbide gallium nitride as a power switching device, at least 50% of the switching loss reduced can be achieved. And that's why the silicon carbide gallium nitride are very promising for the power switching application. In general, the major application for power device can be used for the power supply, telecommunication, electrical hybrid vehicle. And here is an overview of a power electronics application landscape by considering the different voltage rating. And right now, the gallium nitride is mainly used in the low voltage application. Right now, you can easily purchase a gallium nitride based phase charger using for the commercial electronics. So this is a gallium nitride based consumer phase charger. Also, people try to implement the gallium nitride in the data center. And on the other hand, for silicon carbide, I think the most important application for silicon carbide now is using as a traction inverter inside the electrical vehicle. So therefore, the silicon carbide voltage rating right now in the commercial device is ranging from 600 volt up to 1.7 kilovolt. But when we consider for the reliability challenge here, first, I would like to use the infinite viewpoint to explain the reliability challenge. So this is the same voltage rating for 600 volt and then same on resistance, but this is a chip size scaling from the early 19 until right now. So we can find out that with a different technology evolution, for example, superjunction or wide bandgap, even for the same voltage rating, same resistance, what we can achieve now is a smaller chip size. Right now, for the latest generation of the GaN power device, I think the chip size is already 100 times size smaller than the standard MOSFET. So that means the chip area is already reduced more than 100 times. But the major challenge will come from the die size shrink. For example, since we want to deliver the same power density, so once the die size reduced, we'll have the higher power density, higher current density, high electric field. And these all will create the additional reliability challenge. For example, the dielectric challenge and the GaN oxide challenge, or the material quality challenge also will happen. So therefore, we need to understand failure mechanism and in the end, the lifetime impact. So the failure mechanism and lifetime impact, that's also already mentioned in the beginning of this class as being the reliability investigation analysis. The failure mechanism and lifetime is always a key term we will be continually mention and try to understand. So here is another slide to describe the main difference between the gallium nitride power HANS and silicon carbide power MOSFET. So basically, gallium nitride HANS is an electrode device. There's no doping involved. So we have a strong two-dimensional electron gas in here. And the high probability in this interface is mainly due to the polarization difference between the spontaneous and piezoelectric polarization. But the silicon carbide MOSFET is a vertical device as shown here. And the structure is very similar to the silicon MOSFET. And therefore, we need to have a doping is needed to form the PN junction here. So you can see there are many N and P have to be formed to fabricate the high voltage silicon carbide power MOSFET. And here is also the summary slide far from the Infineon's point of view with a different power device technology. Infineon has a product for the cool MOS, that's a silicon superjunction MOSFET, cool silicon carbide, that's a silicon carbide MOSFET, and also cool GaN, that's a gallium nitride HANS here. If you look at for this spider diagram, you can find out that based on the analysis that come from the Infineon, they feel like the gallium nitride is the one which has the worst robustness, and therefore reliability is always a challenge in the gallium nitride. And that's why in this lecture, I will talk about the reliability issue in the gallium nitride. So first, I would like to introduce the sensitive area of the GaN technology. So if you look at the typical operation, this is typical schematic for the hot switching operation for the power device from off to the on. And then this will continue switching between these switching locus. And therefore, our device has to understand the reliability issue also based on this bias condition. For example, in the off state, we have applied very high electric field. And therefore, it could have the trap generation in the buffer, also gate edge degradation because we have very high electric field here. And also we have the electron trapping here because of the high electric field. And in the case of the semi-on, because we apply the high electric field plus a high current, so for sure we also start to suffer the high electron degradation. And because it's still under the high field bias, so we can have the electron trapping. And in the case of on-state, that's mainly focused on the gate side reliability. So we can have, for example, TDDB and interface charge can both happen. And here is another reliability summary come from literature. So in general, if you look at for this reliability summary, we have the off-state, on-state, semi-on-state, and there are many different degradation, including dynamic on, VTH shift, time dependent, and also VTH shift and on shift. And there are many different physics in origin and testing methodology. And therefore, I summarize these reliability challenges shown in here. The main reliability challenge can be divided by off-state. They can be the two main issues. One is the dynamic on, or sometimes we call the current collapse, or the off-state can cause the threshold voltage shift. And that's mainly due to the on increase due to the trapping in the buffer or service, or threshold voltage shift due to the trapping under the gate. Or when we're under the high voltage off-state, they can have the time-dependent breakdown as well. And this will mainly due to the buffer leakage and in the end leading to the breakdown voltage decrease. And in the case of the on-state, we will have the threshold voltage instability, which is similar to our BTI discussed before. So we have the PBTI and BTI we need to have to be considered. And also under the party gate bias, we will suffer the time-dependent gate dielectric breakdown as well. So we need to evaluate the gated current and forward reverse TDDB issues. And in the case of a semi-on, this is combined with a high current, high electric field. So we need to understand the Hall carrier effect. And also recently, more and more literature discuss that during the real Hall switching in the semi-on region can cause severe degradation. So the Hall switching stress can be also one of the main reliability challenges. So first, I will start to talk about the off-state, the reliability issue in the off-state. The first one I would like to discuss is the most important challenge is a dynamic on, or we call this as a current collapse. So this is a fresh IDVD curve. And after one high voltage off-state and you characterize IDVD, then you will see the current decrease. The current decrease means the on increase. So therefore, on is increased after the high voltage off-state. And here is another experimental result to showing that the black one is a measure from the fresh condition without any stress. And the red one is a measure from the after the stress. You can see after the stress, the current obviously decreased. That means our on resistance increase. So in general, this phenomenon is called as a dynamic on. So dynamic on is mainly due to the following three possible reasons. One is a service trap, second is a buffer trap, and third one is a preservation. And dynamic on also depends on how long the device is biased in the off-state, how fast the device is measured in the on-state, temperature, and also electric field distribution. This is also one of the experimental results. You can see this is under the fresh condition, but after operating in the -8 volt, 600 volt, the current is almost disappear. That's why sometimes we also call this as a current collapse, because the current is completely disappear after the certain stress. And there are many literature trying to discuss with dynamic on. And the first literature was reported in the 2001. And this was the first one to propose to explain the dynamic on in the Schottky gate head. And the concept is called the virtual gap, which is a trapping between the gate and drain region. So once during the off-state, we'll apply negative gate bias here. And the negative gate bias will lead into the injection of electron. So electron can be flow into this surface and then can be captured by this surface state. Once captured by this surface state, this electron will stay here and create an additional depletion region here. So as mentioned, depletion of the two that caused by the occupied surface state. So therefore, you can think about that there's another virtual gate come here to deplete our two deck here. And that's why our on resistance is increased. And also one of the phenomenon, very obvious phenomenon for the dynamic is also the partial recovery. This is a summary of the literature with respect to the dynamic ion versus different voltage. You can see, for example, this curve. The ion is increased very fast at low voltage, but in the end is decreased at the high voltage. So ion is not increased at a high bias. The partial recovery is also observed in the dynamic ion. And the dynamic ion is mainly related to the buffer doping. And usually for the power device, we need to have very higher carbon doping concentration. That's mainly for the low leakage current. So this is an experimental result. You can see the GaN with a different carbon doping concentration, with a purple one, which is a higher carbon doping. And then higher carbon doping can give us a higher breakdown voltage. But the carbon doping also in the end will lead to the poor dynamic ion. This is because the carbon can capture electrons here. So this is another experimental result showing that the x-axis is a breakdown strength, the y-axis is ion. So you can see as we increase our carbon doping in the buffer, the breakdown strength can increase for sure, but our dynamic ion is also increased. So when design the buffer of a gallium nitride, it's very critical to find the balance between the carbon doping and also the dynamic ion. And because once we apply in off-state, we have to apply very high drain bias. So we need to apply very high drain bias here. The high drain bias, but the substrate will be ground. So there is a possibility to form the leakage current in the drain to the buffer here. So that's also need to consider buffer time-dependent breakdown. So this is one of the experimental results showing that when we stretch at the VDA 800 volt and chuck at the 0 volt, there's obvious buffer breakdown can observe in this case. And similar to our gate TDD, we can do the Weibull analysis. In the end, we can also extrapolate the lifetime to prove that our buffer is stable enough for the certain operating lifetime. So in this case, with considering the 20 years here, so that means the buffer can operate at least beyond 500 volt.